Alright, it's time to apply the torsion formula and the angle of twist formula to start solving some engineering problems. Now, again, I want to stress the importance of safety here, so go ahead and grab your swim safety goggles, just like we do in our lab. We have our safety glasses, and let's go in search of the pool. Alright, I'm in search of that pool. It's beautifully sunny out, hot. I'm ready to hop in. So let's hope we can find it soon. In the meantime, why don't you hop into this example problem. So in this example problem, we wish to calculate the angle of twist for the steel rod at points A, B, and C. The diameter of the rod is 1 inch, and it looks like it's steel with a shear modulus of 11,500 KSI. So I'm going to start with equilibrium, and so I feel like I need to finish out my free body diagram here. If I have the torques applied, I think I can quickly see that the torque at A needs to be applied clockwise, and it's going to be a value of 2,000 pound-inches. Now, if you don't see this immediately, you can go ahead and do a sum moments. So I'll draw in my x-axis, and we'll sketch in that, and then we'll sum our moments about the x-axis, and you'll see that doing equilibrium, summing moments about the x-axis, we can solve for the support reaction is 2,000 pound-inches. Once we've solved for the torque at A, we can go ahead and draw a torque diagram for rod ABC. So I'll draw my torque diagram along the x-axis once more. And I'll label points A, B, and C along this diagram. When drawing my torque diagram, I wish to use my rules. So if you go back to the first video of this lesson, you'll see that we developed some rules. And we said that when we had clockwise applied torques, this caused a jump up in our torque diagram. So the torque at A causes a jump up of 2,000 pound-inches. And that leads us to a positive or counterclockwise motion. The torque at B is counterclockwise applied, and that leads to a negative shift in our torque diagram. That negative shift is 3,000 pound-inches, so 2,000 pound-inches minus 3,000 pound-inches brings us down to negative 1,000 pound-inches. Then we get to point C. At point C, we have a clockwise applied torque. This brings us back up to 0 at point C. I've gone ahead and added my sign convention, so positive is counterclockwise, negative is clockwise. All right, next, I'll use my second tool in my engineering toolbox, and that's kinematics. In kinematics, we relate displacements. So when we're talking about torsion, displacements is angle of twist. Okay, so that is our correlation back to one-dimensional behavior. Likewise, when we talk about material law for torsion, our correlation is the material law for angle of twist. So angle of twist is phi, and that is equal to TL over GJ for any given segment. So for segment I, so phi I equals TL over GJ of segment I. We'll use the material law and all the kinematics relationships that we develop for the displacement at A, B, and C. So I'll start with the rotation at A. Phi at point A is 0 because it's a fixed end. So I think that's obvious. A is a fixed point, and so the rod is not rotating at point A. So we're fixing that rotation at A. So, got the first answer done. Quick. All right, let's get on to phi at point B. So like we did for axial forces, the total angle of twist at point B is going to equal the angle of twist at point A, our fixed location, plus the change of B relative to point A. So I like to think in these kinematics conditions, as I work with a statically determinate system, I can kind of work from the side that's fixed and work myself away to come up with the deflections. So this is going to translate to be the angle of twist at A plus the TL over GJ that's occurring on segment AB. We already know that the angle of twist at A is 0, so now I just need to evaluate TL over GJ for segment AB. Now when I go to plug in the torque for segment AB, always use the torque from our torque diagram. Okay, we went through all that trouble to draw the torque diagram. Let's use that thing. So the torque on segment AB is 2,000 pound-inches. And I want to convert that to kip inches so that it'll cancel with my variable g in the denominator. L is the length of segment AB. If we look at our problem geometry, we see that that length is 10 inches. G is given to us for steel. It's 11,500 KSI. This is the modulus of rigidity, or the shear modulus. And lastly, we have J. J is the polar moment of inertia. Now, we want to go ahead and calculate J. We can go ahead and put the calculation right in this formula if you're comfortable doing that. But since this is our first time doing an example problem, I'm going to write the polar moment of inertia separate so we can see how to do this calculation. So we said that the polar moment of inertia J for a circular rod was pi over 2 times the outer radius to the fourth minus the inner radius to the fourth. Okay, now in this particular case we have a solid rod, and so our inner radius is going to be 0. So J is going to be pi over 2 times the outer radius to the fourth. The outer radius is 0.5 inches raised to the fourth, minus the inner radius, which is 0. And I just want to draw your attention to the cross-section again. So remember, the cross-section gave us the diameter. The diameter was 1 inch. That means the radius is a ½ inch. Okay, the outer radius from the center of gravity, the middle of the cross-section, to the outmost point, the outer radius is 0.5 inches. The inner radius, since this is not hollow, the inner radius is just 0. All right, so that gives us our formula for J. We can go ahead and punch that into our calculator. We should get that J in this instance is equal to 0.098175 inches to the fourth. Okay, so this is our calculation for the polar moment of inertia. I encourage you to keep a good number of decimal places because in the formula TL over GJ, we use a lot of large numbers and small numbers at the same time, so it's good to have the accuracy on our decimal places. All right, doing this calculation, plugging it in, we'll see that kips will cancel with kips in the denominator. We do all the math, and we get that the angle of twist at point B is 0.017715. Now, what is that, right? Well, I see kips cancel with kips. Let's see, pounds, pounds, inch, inch. If I do a unit analysis, I see that this number has no units. But when we talk about angle of twist, when it has no units, that means it's in terms of radians, okay? And so when we do this calculation, we should end up with a unitless number, but that just means radians. If we want to convert radians to degrees, we know that we can multiply this number by 180 degrees over pi radians. So that converts this from 0.017715 radians to 1.015 degrees counterclockwise, or I'll draw my arrow counterclockwise about the x-axis using that right-hand rule. I hope you were able to follow along with those calculations, but if not, we're going to do it again at point C, give you another chance to see how we can use this angle of twist formula and the kinematics equations to calculate the angle of twist at a particular point. Again, I just want to help you recall what 1 radian is and that conversion to degrees. And finally, I want to stress the point that we always want to use the torque from the torque diagram. So the number one mistake that students typically make when they first see torsion problems is that they like to use the torques that are applied to the system, okay? But that torque that's being applied to the system, that's not necessarily the internal torque in that segment. Because remember, the internal torque in that segment is going to be kind of the summation of all the torques acting along the rod, especially in this case, all of the torques from the free end coming back to the support will affect any given segment along that length. So let's take a look for the calculations at C. So our kinematics condition says that the angle of twist at point C is equal to the angle of twist at point B plus the change from angle of twist on C of C relative to point B. And if we want to extend this further, we can write the angle of twist at point C in terms of the angle of twist at point A. We've calculated the angle of twist at point B, so that's 0.017715 radians. And again, positive because it's going to be counterclockwise. To that, we need to add the change, the angle of twist phi C of point C relative to point B. So this is going to be the value TL over GJ for segment BC. So again, I just kind of keep that first number the same, and now we have to do the calculation for segment BC. Again, I want to reference my torque diagram. I see on my torque diagram that the torque on segment BC was negative 1,000 pound-inches. And again, I'm going to convert that to kips times inches. The length of segment BC was 30 inches. G remained the same, 11,500 KSI. And J remains the same on this segment. And we see that number above, 0.098175 inches to the fourth. So doing my math on segment BC, I get a total angle of twist on segment BC of a negative 0.026572 radians. Okay, the negative sign just means that it's rotating clockwise. So point C relative to point C will be somewhere clockwise of point B when we're looking down the x-axis. When I add these two values together, I see that I have 0.017715 minus 0.026572 radians gives me a negative 0.008857 radians, or a negative 0.507 degrees. The negative sign indicates that it's clockwise rotation, so the total angle of twist at point C relative really back to point A, but if we were to draw a point along the cross-section at point C, after we apply all of these torques, we would expect that that point would have rotated clockwise by 0.507 degrees. I hope that makes sense for the angle of twist along the length of the rod. Let me just reiterate that point at point C. So again, if I consider a straight line from A to B, I saw that my rotation at point B was counterclockwise. So I'm expecting that line to have shifted. And as I look down the x-axis towards point A, I would expect that line to have rotated counterclockwise. Then as I move back to point C, I'm expecting it to rotate clockwise. And my final answer was clockwise, so I expect my final answer to have ended up clockwise of my original line there at point along that blue line. And I'll zoom in there. This angle here, the final rotation of the point there, this angle is the angle of twist at point C, phi C, that we calculated in this particular problem. All right, we'll get better at these as we do more practice with them, but go ahead, take a look at the next example to apply the torsion formula. Well, I don't know where this pool is. You would think I would know this place better by now. Anyways, hope you had fun solving that example problem. Maybe we'll find the pool in our next problem. Go ahead and take a look at the next video.